Hello and welcome to our lesson on section 7.2 for our trigonometry class. In this section, we're going to be covering the inverse trigonometric functions continued. Specifically, we're going to focus on the secant, cosecant, and cotangent functions, okay? So let's get started. First of all, I've got some information here for secant and the inverse secant, and give you a second to pause the video, write that down if you want to. Now we're going to go to our Desmos, and notice that here I've got the secant graph over here on Desmos, but I have the domain restricted according to the restrictions that are required. And let me see if I can explain why that is, okay? If I remove that restriction, notice that the secant function is definitely not one-to-one. It does not pass the horizontal line test. So in order to find the inverse secant, we're going to need the secant function to be one-to-one. And that's why we need the restriction on the domain. So the way that you decide how to restrict the domain, first of all, you have to accommodate every value of the range. That means you can't restrict it too much so that you lose content, but you have to restrict it enough so that it is one-to-one, okay? So notice that these humps, they go down to minus infinity, up to -1, and then pick up again at +1 and go to infinity. So we need to accommodate all of the values of the range and have the function be one-to-one. It has to pass the horizontal line test. And so that's how we come up with this restriction here. Notice we still go from minus infinity up to -1. And we pick up at 1 and go to infinity. So all the range are accommodated. And if you do the horizontal line test, you'll see that this function is now one-to-one. Okay, so I hope that explains why we have to have the restriction and why it is what it is. Okay, now I would like to also draw your attention to the fact that even though we restrict the domain from 0 to pi, there is a value in there that is not going to be allowed, and that's because there's a vertical asymptote. So if we go back to our OneNote, you'll notice that the domain is from 0 to pi over 2, not including pi over 2, and then it picks up at pi over 2 and continues to pi. So do you see how we get that? The domain here starts at 0 and goes until we hit pi over 2, and that value cannot be included because of the vertical asymptote, but it will pick up on the other side of pi over 2 and go all the way to pi, okay? So that's how we get from this notation for the restriction to the interval notation for the domain, okay? Now, obviously, if you know anything about inverse functions, you know that the domain of the original function is the range of the inverse function. So these are identical. And the range of the original function, going from minus infinity up to -1, which is included, and then picking up at +1 and going to infinity, that's going to be the domain of the inverse. Okay, so let's take a look at that. Here's our secant function restricted. I do want to go ahead and sketch the line y equals x so that you can see the symmetry of the inverse function, okay? So notice the symmetry about the orange line of the black and green graphs. If you fold across the orange line, the black and the green line up with each other, okay? That's the kind of symmetry that any function has with its inverse. And so this helps us identify that this inverse function is really the inverse of the secant. All right, so now that we've talked about secant, the domain and range of the secant and the inverse secant, let's talk about cosecant, okay? So if we go back to our graph, and if we turn off the secant, let's talk about cosecant, okay? Here's the cosecant graph with the domain restricted. And again, I'm going to remove that so that you can see the cosecant is really not 1-to-1. And so we have to place this restriction on the cosecant so that it accommodates every value of the range and that it is 1-to-1. Also notice that at x equals 0, there is a vertical asymptote. So the domain for the secant here, not secant, the domain for the cosecant should be everything from negative pi over 2 up to 0, and then from 0 to pi over 2. And that's what we have for the domain here. Everything from negative pi over 2 up to 0, not included, and then picking up at 0 and going to pi over 2. Again, the domain of the cosecant is the range of the inverse cosecant, okay? And then the range of the original is the domain of the inverse. So if we go back, we've already got our y equals x graphed. Let's look at the inverse cosecant. And again, you should see the symmetry, the folding symmetry along the orange line so that the black and the green match up. That is a thing of beauty. Yes. So here again we have the restrictions on the domain and the range for this cosecant. That's how we get this information. And now let's go and look at cotangent, okay? So if we go back to our graph, we turn off the cosecant graphs and look at cotangent. Now again, notice I've got the domain restricted from 0 to pi. If I take off the restriction, you'll see that the cotangent function is definitely not 1-to-1. And so again, we need to restrict the domain so that we accommodate every value of the range, but also so that the function is 1-to-1. And so that's how we come up with this restriction. Notice for this function, there is no vertical asymptote, so the domain should be everything from 0 to pi. However, if we remove that restriction, notice that there is an asymptote at the endpoints. At 0 and at pi, there's vertical asymptotes. So when we place that restriction on there, notice that it's strictly greater than 0 and strictly less than pi. It's not equal to because of the asymptotes, okay? If we go back to the notes here, you'll notice the domain has the parentheses, meaning that those endpoints are not included. And the range does go from minus infinity to infinity. It goes all the way down and all the way up. So again, if we look at the inverse cotangent, again, we should see the symmetry about the line y equals x. And you'll see the domain and the range of the inverse cotangent matches the flipped domain and range of the cotangent, okay? And so that should pretty well cover the, I guess, the introductory content. What we need to do now is we need to look at some specific examples, okay? So let's go to our textbook. The first example we're going to start with is we're going to have the inverse cotangent of square root of 3. And the instructions say find the exact value of the expression. Now, in the previous video, we talked about how an inverse trig function produces an angle. So an inverse trig function is always equal to some angle theta. And then if I want to solve this for theta, I'm going to bring the inverse cotangent to the other side, which is going to turn that back into regular cotangent, okay? So we're going to have the square root of 3 equals cotangent of theta. At this point, we're going to use a reciprocal identity, knowing that the reciprocal of cotangent is tangent. So if I flip the cotangent, I get tangent, which means I need to flip the other side, which is going to give me 1 over square root of 3. And then if I rationalize, that's going to give me square root of 3 over 3. Okay, so now what I'm looking for is, in the unit circle, I'm looking for what angle theta within the appropriate range of values. And remember that the inverse cotangent is restricted to angles from 0 to pi. So we are restricted to angles from 0 to pi. We want to know what angle within that range of values has coordinates such that y divided by x produces square root of 3 over 3. And I believe that angle is going to be at pi over 6. Okay, so let's check that real quick. If this is my x and my y, and I need to do the reciprocal of x times y. 2's will cancel, give me 1 over square root of 3, which is equal to square root of 3 over 3, which is the value that I needed. Okay, so the answer to this problem should be pi over 6. Okay, and that's it for the first example. Now let's go look at another example. Okay, let's look at the inverse secant of negative square root of 2. Okay, again, we know that an inverse trig function produces an angle theta. And then if I bring the inverse secant to the other side, that's going to turn it back into regular secant. Again, I'm going to use a reciprocal identity. I know that the reciprocal of secant is cosine. So if I flip secant, I get cosine theta, which means I need to flip the other side and rationalize. And so at this point, I'm looking for what angle theta within the appropriate range of values. Okay, we're looking at inverse secant. And if we scroll back up, we're going to see that inverse secant is restricted from 0 to pi, not including pi over 2. Okay, so again, we're looking for angles from 0 to pi, not including pi over 2, where the x coordinate, remember cosine theta is x, is negative square root of 2 over 2. Okay, and that's going to be right here at 3 pi over 4. So again, this answer here should be 3 pi over 4. The answer to that problem should be 3 pi over 4. And that's it for that example. Okay, let's look at another example. Okay, let's say that we have inverse secant of 4. Okay, now this time it says use a calculator to find the approximate value rounded to 2 decimal places. So this time we're going to be able to use a calculator, mainly because this value is not going to be in the unit circle. So to start with, this is equal to some angle theta. Again, we're moving the inverse secant to the other side, which will turn it back into regular secant, and then we're going to use another reciprocal identity. So if I flip secant, I get cosine, but if I flip one side, I got to flip the other, so that's going to be 1/4. And now what I want to do is I want to bring the cosine back over and turn that into inverse cosine of a fourth, which is going to give me something that I can input into the calculator, okay? So now I can do inverse cosine of a fourth equals, and that's going to give me 1.32 rounded to 2 decimal places, okay? 1.32 rounded. And that's going to be the answer for that problem, okay? Again, if I need to verify that, the inverse secant, remember the inverse secant was restricted from angles from 0 to pi. And from 0 to pi, those are positive angles, really from 0 to 3.14, if you look at what pi is approximately. And so then the question becomes, is our answer, is 1.32 a radian angle from 0 to 3.14? And yes, that is true. So that helps us feel better about the answer, okay? All right, I think we should look at another example. And this time let's go with purple. Example. Let's say we have the cosine of the inverse sine of square root of 2 over 2. How do we tackle this problem where we have composite trig functions, okay? So for this example, the first thing we need to do is we need to say that an inverse trig function is some angle theta. And then once we decide what that angle is, then we're going to come back and we're going to figure out cosine of theta, okay? So this is almost like a two-part problem. You have to determine what theta is so that you can find cosine of theta. And so we're going to bring that over here to the side. We're going to say theta is the inverse sine of the square root of 2 over 2. And then at this point, we're going to bring the inverse sine over, which will turn it into regular sine. And so now we're concerned with, well, where in the unit circle do we have an angle theta such that the y-coordinate is square root of 2 over 2? And I think most people know at this point that that's pi over 4, okay? That's 45 degrees, where our y-coordinate is positive square root of 2 over 2 is when theta is pi over 4. And so now that we know what theta is, now we can find cosine of pi over 4 by going to the unit circle and looking at the x-coordinate at pi over 4, which is square root of 2 over 2, okay? So the answer to this entire problem should be square root of 2 over 2. We are going to calculate that with the calculator just to verify. So we have the cosine of the inverse sine of square root of 2 over 2, and with our handy dandy Casio, that should verify the answer. Bam, just like that. Oh yeah, calculator, freaking sweet. All right, let's do another example. We're going to do several examples here, okay? Next example. Let's say we have the secant of the inverse tangent of a half. The secant of the inverse tangent of a half, okay? So where are we going to start? We're going to start at the same place that we did on the previous example, knowing that an inverse trig function equals to some angle theta. And then once I determine the characteristics for that theta, then I'm going to come back and figure out what secant of theta is, okay? So again, this is like a two-part problem where we're going to start and say theta is the inverse tangent of a half, and then we're going to bring the inverse tangent to the other side, and that's going to say tangent of theta is a half, okay? Now, at this point, this is not from the unit circle, so we're going to have to do a little bit more work. Knowing that tangent theta is y over x, we can now see what x is and what y is. If I know x and y, I can find r using Pythagorean theorem, okay? So x squared plus y squared equals r squared. Substituting, 2 squared plus 1 squared equals r squared. That's going to be 4 plus 1, which is 5. And then r, if I take the square root of both sides, r is going to be the square root of 5. So now at this point, now that I know x, y, and r, I should be able to find any trig function. Remember, secant is the reciprocal of cosine. So if cosine is x over r, secant is r over x, which should be square root of 5 over 2. And that should be the final answer for that problem, okay? So there's that example done. And I believe we've got one more example to work through, and then we're going to call it good for this section, okay? Let's say that we have the cosine of the inverse tangent of u. Now, these instructions say write each trigonometric expression as an algebraic expression. We're going to have to convert this from trig functions into just an algebraic expression, okay, with no trig functions at all. So again, where do we start? Same place as we did in the last two problems. Inverse trig functions always produce an angle. So here we know that theta is the inverse tangent of u. And then if I bring the inverse tangent back to the other side, that's going to say tangent of theta is u, which I can express u as a fraction by putting it over 1. And I know that tangent is y over x. So this tells me that x has a value of 1 and y is u. And just like I did in the previous example, I'm going to use the Pythagorean theorems to find out what r is. So we're going to have x squared plus y squared equals r squared, which is going to give me 1 squared plus u squared equals r squared. And 1 squared plus u squared, if I switch those around just because I feel like it, that's the same as u squared plus 1. And then if I take the square root of both sides to get rid of the squared, I'm going to have r is the square root of u squared plus 1. Okay, so now I know what r is, and I know what x is, and I know what y is. So now I should be able to calculate any trig function, and we need cosine, okay? Because it was cosine of the inverse tangent of u, but we said the inverse tangent of u was theta, right? So really we need the cosine of theta. So down here, the cosine of theta, remember the cosine ratio is x over r, where x was 1, and r is the square root of u squared plus 1. Okay, so far so good. Now, if you want to stop there, that's okay, even though there's a square root in the denominator. If you want to rationalize that, that's fine too. Rationalized, that should be the square root of u squared plus 1 over u squared plus 1, okay? But this right here would be acceptable, and so is this. And that's going to do it for section 7.2. So if you have any questions or comments, feel free to leave those in the comment section below, or you can text me. And thanks for watching.